So I was very interested to read this book, In the Enemy's House. As you probably know, the perfect cryptographic system is the one-time pad. In the one-time pad, you have a page of random letters, and the person at the other end has the same page of random letters, and each letter you use to encrypt one letter of the stuff you're trying to encrypt. And it could be you use any simple system, like even the Caesar cipher or anything, but you encrypt each letter based on a different key, and there's no pattern in the key. And therefore, nobody can decrypt it. And this is appears known for hundreds of years, and no one's ever found any flaw in it. In fact, the argument seems very clear because you have random letters of ciphertext, and if you decrypt them by randomly decrypting every letter, you can create every possible message of that length. So even if you were able to do a brute force attack and try all possible decryptions, you would just get thousands of readable messages that said anything you want. And you have no way to tell which one is true, which, by the way, we were talking before about how when it tried to decrypt substitution cipher, thinking it was Caesar cipher, why didn't it notice that the end result was still unreadable garbage? And usually, when you're trying to decrypt something, all the wrong keys make garbage and only the right key makes readable English. So you can detect that. But in this case, many of the wrong keys will also create readable English. You have no way to know what the message is. So that's the perfect system that we would like to all use. The problem is it has a huge key distribution problem. You have to get enough key to the other person that is longer than all the messages you're going to send. So you have to give them whole books full of random letters. And there are a few computer systems that use this, but it's really quite rare. But it's useful to understand because essentially all modern cryptographic systems are an attempt to create this one-time pad system with using a pseudo-random sequence derived from a shorter key so it's easier to distribute. So another problem with the one-time pad is, besides the key distribution problem, something that is not obvious at all. When the Russians in World War II were using this, they didn't have enough keys, so they would put in more copies of carbon paper and make like 4 or 5 copies of the key and use the same one-time pad more than once, not knowing that when you do that, the whole system shatters like glass, and it turns from the perfect unbreakable system into one that's trivial to break even without a computer. It's amazing, and that's what we're going to do here. So we'll start with a one-time pad. I'll use GoGo Colab just because it's a nice Python environment that every student can get and will always be the same. Any other Python environment would be fine. All right, and so here's some Python code that will encrypt this. Let's put that in. I'm trying to paste. Why is there no paste option? All right, there it is. So here's the key. Unbreakable, awesome, secret, secure system. By the way, it would be better if the key was just random letters, but in this case, it's a readable sentence for no good reason. Here's the plain text. And all it's going to do is each letter, it's going to move it, do what I said, the Caesar cipher. It's going to move each letter forward by an amount related to that letter in the alphabet. So if you run that, it will, yes, there we go. Okay. So F is 46. This is the key, unbreakable. That's you. And so it XORs these two. That's what it does. XORs these two to create a encrypted version. And the key for the XORing keeps changing. So you get this series of hexadecimal digits is the encrypted code. That's a perfectly fine system. All right. And if you want to decrypt it, you just do the same thing backwards. So that would be down here. All right. That's just going to reverse the process and see this XOR that gives me the FOUR. And so you get the plain text on the right, 4 and 7. So that's what basically goes on here. And now in this case, you're encrypting and decrypting and you know the key. But it turns out if you use it twice, you don't need the key. And that's what goes on here. That's called the crib drag attack. And so here's two ciphertexts that were encrypted with the same key using this technique. And the way you break it is you start with a guess. So that's the crib drag attack. And I've got a script to demonstrate this. get people started off here. Here's a Python script that will let you guess. So let me put this in and let's play with this. I'm not sure about the interactivity of it in this environment. We're going to see how well it works. All right, but the point is, here are the two encrypted ciphertexts in hex, and you start with a guess of the key. So I'm going to guess that the key contains the word "the" somewhere, and I'm just going to put dots for all the letters I don't know. And now it's just going to have an endless loop where it's going to decrypt both of these messages based on the current key and show it to you. And then it's going to let you guess a letter in either the key or one of the plain text messages, and then do it again. And that's all. And this is the crib drag attack. You guess a word to get a few letters to start with, and you'll see what happens. Whoops, I just want to run this there. Okay. All right. So now I guessed the word "the," and here I have "nev," and here I have "you." So that strongly implies that the first three letters are correct, because if they were wrong, this would turn into unreadable binary gibberish like that. So this looks like the word "the." Now I think the next letter here could be "these" or a space. This could be the word "never." "You," this could be "you" and an apostrophe. So I think I'll start with the key and guess that there's a space in location 3. So key location 3 is a space. So now it's going to do that. And now see this word, that turned into a readable thing here, an apostrophe after "you." So this is probably now the word "never." So I can guess that P1 has an R in location 4. The first plain text has location 4 is an R. And now this is UL. So now I can see P2 location 5 is an L. So 2 location 5 is an L. And after that, there must be a space. So P2 location 6 must be a space. And so on. You can now, this is how it works. You guess back and forth among these three things, and you can decode it. It's surprisingly easy, doesn't really require a computer or anything. And that's called the crib drag attack. And it's the flaw with the one-time pad. It's perfect if you use it just once, but if you use it twice, it shatters down to being essentially useless. And I've got some various tougher ones to do here. So I thought that was fun. Stop this recording.